Cool. So okay, let's one other thing I wanted to discuss briefly related to noise shaping. So in a noise shaping, all you want is this, right? Let us say in Z domain, if I write, my output must be the input, plus if it is a first order noise shaping, what do you want for the quantization noise? Q of Z times what for first order noise shaping? Into 1 minus Z inverse, right? And we sort of obtained this operation. I mean, this is what you want inwards, and in circuits we got implemented in couple of ways. One was the error feedback and one was delta sigma modulator. But of course you can, once you have an idea of what needs to be done, you can come up with multiple things to do the same, right? And let me motivate you for one such implementation. Let us say in principle you have access to both U and Q. Assume that both are inputs, that both are two inputs, right? At the output I want this fellow. So what is the simplest way in which I can realize this if I have access to both U and Q?
Multiply Q by 1 minus Z.
Right, that's all. This is the most straightforward thing one can do. Unfortunately, you don't have access to Q. So in error feedback, we sort of got an estimate of Q by taking the output minus input and did blah blah blah. But let us say I don't do that, and I do the following instead, right? I know for a fact that Q is not something that is under your control. It directly adds to the ADC output or ADC input. So I'll try to push this 1 minus Z inverse away from this. Okay. So if I push this out of the summer, what will happen?
U should be divided.
Yeah, here what will happen?
1 minus Z.
Here it is 1 minus Z inverse, and that makes sense because now Q is multiplied by 1 minus Z inverse.
This time we have to 1 by Z.
Yeah, here I'll have to do 1 by 1 minus Z inverse, that's all. Fine. So the input is first divided by 1 minus Z inverse, multiplied by 1 minus Z inverse, we get it. Right, so let me push it to the next page. So the natural question is, why not do this? Looks much simpler, no negative feedback, nothing. So what do you think? Do you think this will work, or in practice do you think this will work, or do you foresee some issues?
Can we implement 1 minus Z inverse?
It's an integrator, right? I mean, this, okay. Oh, see, here is the output of the ADC, right? Sorry. Here is the output of the ADC. It's a digital number. Right? Subtracting one number from previous sample, it's trivial. There is nothing. What is this block? 1 by 1 minus inverse. What operation it is doing?
Integrator.
It's an integrator. Yeah, that's okay. But I am using an integrator in open loop. Do you foresee any issues because of that?
It will not make DC equals to 0.
Okay, that is fine. But let us say if the input has a DC, what do you think will happen?
It cannot be infinite.
Yeah.
This will go to infinite, right?
Yeah, if the input is DC, the output will sort of ramp up, and finally it will saturate your supply voltages, right?
Yeah.
I mean, that's why in practice you never see open loop. I mean, integrators used in open loop. And for that matter, if you design an op-amp with infinite gain, an op-amp with infinite gain is useless in open loop, right? Because infinite gain, what do you do? The reason you have infinite gain, why do you have infinite gain?
Make it virtual ground.
You want to have negative feedback systems. Because you want to enforce a strong virtual ground. That is why you have all this infinite gain. So that is why you can't have this guy in open loop. So in other words, I will say if you implement a voltage integrator like this will not work. But let's not lose hope.
But if in ideal world this U has 0 DC, that we.
But that is also not good, right? Because remember, we are interested in digitizing very low frequencies. This is noise shaping, right? It need not be exactly 0. Even if it's a very low frequency, we are screwed, right? So you will never use a voltage integrator in open loop like this, or for that matter, current integrator. So let's see if something else can be done here. Okay, so okay. So let us say, I mean, or do you know any quantity I mean, if with respect to voltage or current, the issue is after some point it saturates the supply you have, right? DC input voltage, the integrator output will saturate to your voltage later. That's the issue. Now, do you know any quantity that in principle doesn't saturate? It's not voltage or current, obviously. Any other quantity that have you heard of that doesn't saturate? Or I'll say after reaching some maximum value, it wraps up to a small value and some quantity that increases, let us say, but after reaching a maximum value, you can round it off to minimum value and start again. Something like that, have you heard of?
I'm saying all the VCO.
No, but
No, I don't.
okay. What I'm saying is something should keep increasing, and after something it should come to it should wrap around. So it should operate in some kind of modulo operation. Any quantity you remember that operates in modulo arithmetic? Okay, phase, have you heard? Phase of a signal. Okay, so okay, maybe I probably have to do this. So let us say you have something, right, cos 2 pi f naught t.
Plus 5.
That's okay. What is the phase in the signal? No, actually, okay, strictly speaking, that is additional phase. This is the phase actually. Okay. So, I mean, you can define the phase of the signal to be this 2 pi f naught t. Okay. And here, let us say if you look at the phase here, so after reaching 2 pi, what do you think will happen? It will wrap around. So, in principle, I mean, or I don't even have to wrap around, it can go anywhere, right? It can go from 2 pi, 4 pi, 6 pi, anything. In principle, this doesn't saturate, isn't it? And one thing to notice, if let us say, if I say a phase of 2 pi, if let us say I say this guy finishes a phase of 2 pi, what does it mean for the voltage waveform? If it completes one cycle, I will say phase is 2 pi, 2 cycles, phase is 4 pi, and so on, right? So this is something you'll know, I guess. This is one cycle, 4 pi is 2 cycles, and so on. So the point I'm getting at is, if this were a phase signal, the saturation issue is not there. Again, it's all like very hypothetical case. Let's stick to the hypotheticality for now.
Basically, you're saying that in one time period the area is 0.
Not really. I mean, phase is a, it's not a real signal. It is something that you infer from voltage or current signal, right? And that phase in principle doesn't saturate, right?
Yeah.
So if let us say this were a phase signal, it is okay. So, okay, maybe this also, I don't know. If the output of an integrator is phase, what do you think will be the input of the integrator? Integral of what quantity gives you phase? You guys are aware of? Or let's say look at this is the phase. Here what is the frequency? F naught.
It will be the phase itself.
No, hold on. So here this is the phase, right? Here what is the frequency? F naught. Frequency of the signal is F naught, right?
Yes.
So what I am saying is the frequency is constant. I have a constant frequency. What is the phase? 2 pi f naught times t. Frequency is constant, but what is the phase? If the frequency is constant versus time, let's say the frequency is constant. How is the phase looking like?
Linear.
So what kind of relation do you think is there between?
Area. Integrator.
It's an integrator. That's a fundamental definition, that if you have a frequency, you integrate it, you get phase. So if this is phase, so what do you think this is?
Constant.
No, I mean, it's a frequency. Integral of frequency is phase. Okay.
I still didn't understand that 2 pi of f naught t is the signal over there.
Right.
That will saturate to VDD, right?
No, this is not a voltage signal, right? This is a phase. It's a hypothetical signal in principle. I mean, this is argument to your cos, right? This is your voltage signal V of t. Oops, sorry. You understand? So this is my voltage signal V of t. I am just looking at the argument of my cos. or for that matter any periodic signal I can take and do this. Simply speaking, any periodic signal is sum of costs, right?
How will you look like that here?
That's what we'll come to that. Hold on. So this till this point it's clear. In principle, if this were a phase, the issue of saturation doesn't happen. And by fundamental definition, the frequency and phase are related by the integral operation. So the input to the integrator must be frequency. Now I want to digitize a voltage signal, right? Because my signal that needs to be digitized is voltage, right? So I have to convert voltage to frequency. So what can I use? VCO. I hinted you in the last class. Again, you don't have to understand how VCO operates. It's just that it is an oscillator whose output frequency, if I call it omega out, is some constant, I will say k VCO times the input voltage V. That's all. And if I look at the phase, it is integral of the frequency. So this is something interesting. So let's look at this. Right, so what I am saying is this: I will apply my input voltage to a VCO. The VCO will convert the voltage to a frequency, and what I should do is I actually don't have to do this integration, because what I am essentially doing is I am looking at the phase here, right? Because fundamentally the relation between frequency to phase is an integral, so you don't have to sit and do integration, right? So what I have to do is this: I give my input to the VCO. I will sit here and observe the phase of the signal here. If I simply observe the phase of the signal, the relation from the input voltage to the output phase is integral here. Okay. So if this signal here I should observe his phase, here remember I will have the quantizer. So this no longer is a voltage quantizer. What quantizer is this? No,
the phase quantizer.
We should quantize the phase. That's the difference.
Where did this transfer of F to 5K happen in this?
No, that's what, right? The definition is this, right? If I have a frequency omega, let us say omega out, if I want to look at the output phase, the relation is this. Okay, I take any signal, I look at its phase, that directly gives me an integral of the frequency. It's something like this, right? If you have a capacitor, the current is integral dt. You don't sit and do the integration yourself. If I apply a voltage and observe the current, that's an integrator, right? Similarly, if I apply a frequency, which I am indirectly doing using this voltage, right? If I apply this frequency indirectly using my voltage through VCO and observe the phase of the VCO, we get the integration.
That happens by itself.
That's a fundamental definition. It is definition, right? You don't have to do anything. It is an ideal integrator. You get an ideal integration for free. That is something like this, right? The analogy is this. You apply a voltage to a capacitor, you observe its current, you get an integrated voltage directly. The same thing happens here. Okay. So I apply the voltage to a VCO and somehow observe the phase of the VCO. And that phase, if I go and quantize, that directly gives me this guy. So at the output, I just have to do this 1 minus the inverse and I am set. Right? So here, of course, 1 minus the inverse is simply subtracting in digital, straightforward. So let's quickly look at what this is phase quantizer. Right? And for that, let me actually use this. Let me take an example and then show. Because once you understand what this is, you will realize how trivial the operation is. So let us say I apply a constant voltage V naught to my VCO. If the input voltage is constant, the output frequency is also constant. Okay, and which means if I look at the phase here, what will be the phase? it's sorry, the phase is basically integral of this frequency. And what is that integral? K VCO times V naught times T. That's the phase, right? So if I basically try to plot the phase here, this is time, this is my phi out of T. It's going to be linear like this. Okay, and let us say I mark these points where it crosses multiples of 2 pi. So what can you say about the corresponding time when it crosses 2 pi?
2 pi upon this.
Yeah, basically it's basically one time period T naught, right? When it finishes one oscillation cycle, the phase is 2 pi. So this is one time period T naught, 2 T naught and 3 T. So if let us say this is V VCO of T, if I observe the output voltage of the VCO, let us say it is a square wave for simplicity. It can be a cos, sine, anything. I am taking square for simplicity. So this will how it look like, right? So let us say it finishes one cycle here, right? So if icing edges come here. Is that okay? So I know that if it finishes one cycle, the phase is 2 pi. If it finishes 2 cycles, the phase is 4 pi and so on. So this is how the signal is going to look like. So let's understand how can we quantize the phase. And for that I'll take you down to this notion of quantizing voltage. So let us say I have an incoming voltage signal. I want to quantize the voltage. So for quantizing the voltage, what I do, I take the incoming voltage, compare with a bunch of reference voltages and then do it. So I will say that if the voltage is lying between 0 and VR, it is 0. If it is lying between VR and 2VR, I will say the output code is 1. Okay. So if you look at the operation, I am taking the voltage, comparing the voltage with a bunch of reference voltages and then taking the decision. So similarly for a phase quantizer, what should I do? Inverts. For voltage quantizer, I take the voltage, compare with a bunch of voltage references. For phase quantizer, phase references. Okay. So now the only thing is, how should I choose my phase reference, right? So this is my incoming phase. This is the quantized phase. So I have to choose some reference phases like this. In principle, this can be anything, but remember that the phase is not something that we can visually see, right? This is a hypothetical signal that you are making sense of by looking at the voltage waveform, right? So you should choose a reference phase such that by observing the output voltage of the oscillator, you should be able to understand what that phase is. What is that value of phase that you can understand by looking at the voltage of the oscillator?
The time period of the
Yeah, but what is the phase you can make out from this waveform? 0, 2 pi, 4 pi, right? Because every oscillation cycle corresponds to 2 pi phase. So 2 pi is the only phase you can exactly say by looking at the waveform. So what do you think will be a reasonable reference phase to choose?
2 pi.
So I'll choose my reference phase to be 2 pi. Okay. So I'll just mark it like this. So now this is going to be 2 pi, 4 pi and so on. So the quantized reference is looking like this: between 0 to 2 pi 0, 2 pi to 4 pi 1, 4 pi to 6 pi 2 and so on. So now if you look at what's happening, so the output of this quantizer is 0 till 2 pi, right? Basically what I am saying is, once it becomes 2 pi, the output is 1. So which means once it finishes one clock cycle, or when I get the first clock edge, the output is 1. And once the phase exceeds 4 pi, which means I get the second clock edge, the output is 2. I get the third clock edge, output is 3 and so on. So do you know any kind of block that does this? Not adder, right? I mean basically at every clock edge I have to keep incrementing, right? It's a counter. You give this clock, this is a clock essentially. You give this clock to a counter and it's doing this job for you.
We can keep even the adder and feedback from.
Adder and you need a, okay, I mean,
Clock, okay.
Right? Counter is the simplest thing, right?
Yeah.
So basically if you think about it, this complicated looking phase quantizer, it's a freaking simple counter that you did in second year BTech. Okay, so this phase quantizer is now a simple digital counter.
What is the limit of that function?
Those things implementation I'm not going, right?
Okay.
But at least this is the deal, right? So now the deal is really simple. Take the VCO. You have to observe the phase and quantize the phase. And turns out the digital counter is something that can nicely look at the phase. So here I have the digital output. 1 minus the inverse and voila, you're getting it.
But this counter is for the just square wave, right?
Yeah, you can have an oscillator which is square wave oscillator, right? I mean, even if you have a sine wave oscillator, what is the simplest way to convert a sine wave to a square wave? Or let us say, let us say it's from 0 to.
If it's positive, make it VDD.
Let us say it's 0 to VDD, right?
Then if greater than VDD by 2.
What is the simplest circuit that converts this to this? Huh? No, don't think so much, right? Simplest digital circuit. I mean, what I'm saying, if the input crosses a threshold, it has to become 1. Simplest circuit, I mean, op-amp comparators are all slightly more complicated. It works, I'm not saying it doesn't work. And even simpler circuit. Or let us say, probably I'll give you hint it like this, right? Let us say I want to do this. Let us say when it is high, I want low. Something like this. CMOS inverter? Understand? CMOS inverter, what does it do? If the voltage is greater than your, like switching threshold, right? So basically you just put a bunch of inverters here, you are set. Okay. So this directly gives you a first order noise shaping ADC for free. And you see what are the things you need, right? So you just need this guy, and this is a simple digital subtractor. Take the input, take the digital input, take the previous digital input, subtraction, trivial. Counter, second year you know how to do it. And this VCO is looking the only thing that you might not know, and you know what is the simplest oscillator you can make?
From this inverters only, right?
Inverters, hopefully I don't know if you know, so you can have odd number of inverters and sort of put it in feedback. This works as a simple oscillator. And to control the frequency you can do a lot of things, and it's pretty straightforward to do. So look at it now, to make an ADC you need a digital subtractor, digital counter, and inverter. Again, inverter is a disputed property. Analog people claim it's analog, digital people claim it's digital. But in this context, at least it is used as a digital block. So using truly digital blocks, you make an ADC. Right? And that's the beauty of this. Right? So of course, it looks nice. So obviously, if something looks too nice, something is there, right? So which of these blocks do you think could have issues? There are only 3 blocks here. The last block is a subtractor.
The first, if you are using this one, then gain cannot be analog.
No, gain is a voltage, right? Yeah. Let's look. Do you think something can go wrong here? It's a subtractor.
No.
It's a simple counter.
No.
Something can only go wrong here, right? And what goes wrong is the following. See, here I have assumed that the output of the VCO is a nice linear version of the input, right? In practice, this is never the case. This will be a terribly non-linear function of the input. So that's what limits this. So, but of course, people don't give up. So, if this is non-linear, at the digital end, you put an inverse non-linearity to correct what? Again, digital calibration. If somehow you can characterize the non-linear characteristics of the VCO, you apply different input voltages, measure the frequency, and then get this non-linear function, you should be able to invert that non-linearity at the output. That's something people do. So because of this is also a very commonly done thing now. And now if you look at our verticals, right? So I don't know where it is, all the verticals. Yeah. So now if you look at the verticals we have, so along with this is, I'll say, time domain thing. Now it opens completely new vertical. What is the quantity that is being digitized? So we had always been doing with only voltage. So now we are actually dealing with frequency or phase. Or you can also do with time, time frequencies also. So, again, if you look at it historically, till 30 years back, only 3 verticals were there, right? So, and then people figured this works. Now, not now, but again, similar time, people figured out you can do this also. So now we have a whole bunch of things, and you can play around with everything, right? Now we have so much of options, and different architectures can be developed. So we'll never know. Maybe in the future you'll have one more vertical opening up, and you can have more.